Hello guys, it is time for the Unit 10 and 11 review, so let's get started. Number 1, a large city newspaper periodically reports the mean cost of dinner for 2 people at restaurants in the city. The newspaper staff will collect data from a random sample of restaurants in the city and estimate the mean price using a 90% confidence interval. In past years, the standard deviation has always been very close to $35. So that's the standard deviation has always been close to $35 in the past. Assuming the population standard deviation is $35, which of the following is the minimum sample size needed to obtain a margin of error of no more than $5? So this sounds like we're solving for a sample size. So we have our desired margin of error has to be greater than or equal to our z star times the standard deviation over the square root of the sample size. So again, remember we're using z star because we can't get a t star without the sample size because I would need degrees of freedom. So we're going to go ahead and use that z star critical value. Our desired margin of error is to be within no more than $5. Our z-star critical value for 90% is 1.645. Remember, that number never changes. The standard deviation from the past has been $35, so we're going to go ahead and use 35 divided by the square root of the sample size. Now we're just going to do some algebra here. Our first step, we're going to divide by 1.645 on both sides, divide by 1.645. And what that brings us to is we have 3.0395 is greater than or equal to 35 divided by the square root of the sample size. Remember that at this point, we would multiply by the square root of n and then divide by the 3.0395, which basically just means we're switching these two. So the square root of n is greater than or equal to 35 divided by 3.0395. All right, and now I'm just going to simplify. The square root of n is greater than or equal to 11.515. At this point, I can now square both sides. I'm going to square this side, n has to be greater than or equal to, n has to be greater than or equal to 132.595. So I look at my answer choices, and I'm looking for the number that is greater than 132.595, and that is 133. Again, just need to make sure you're comfortable with the algebra part of that. Your z-star critical value. So remember, your z-star critical value for 90% is 1.645, and your z-star critical value for 95 is 1.96. Most of the time in these kind of problems, it's going to be one of those two. Alrighty, let's move on to number 2. If I can get it to scroll. There we go. All right, for number 2, it says here that we have, which of the following describes a situation where a normal condition is met, therefore the T procedures can be utilized. All right, so let's look at these. N equals 7, N1 is 7, N2 is 7. That means our sample sizes are both too small for the central limit theorem, but it tells us that both samples are approximately normal with no outliers. So those are both okay, so then our T procedures would apply. That would be basically like looking at the box plot. So this one would be fine. N1 is 15, N2 is 5. So again, I need to look at the sample. The sample 1 is approximately normal, so that one's good. Sample 2 is strongly skewed to the right. That is not okay. C, N1 is 15, N2 is 30. So N2 meets the central limit theorem. So N2 is fine, but we need to look at N1. So N1, it says both are moderately skewed. Moderately skewed is okay, but sample 1 has an upper outlier. We are not okay with that. So that knocks out C. N1 is 45, so that means our central limit theorem works. N2 is 30, also our central limit theorem works. Because both of those sample sizes are greater than or equal to 30, then none of this other stuff really matters. The fact that sample 2 has 2 outliers doesn't matter because of the fact that the central limit theorem takes care of this one. So this one's okay as well. Therefore, it is safe to use T procedures in more than one of these situations. All right, C. Popular wisdom is that eating pre-sweetened cereal tends to increase the number of dental cavities in children. A sample of children was, with parental consent, entered into a study and followed for several years. Each child was classified as a sweetened cereal lover or an unsweetened cereal lover. At the end of the study, the amount of tooth damage was measured. Here are the summary of the data. Assume the necessary conditions for inference are met. Which of the following is an appropriate 95% confidence interval for the difference in the mean tooth damage, sweetened minus unsweetened? So it looks like I just need to construct a confidence interval. In order to construct a confidence interval, I'm just going to use my calculator. So I'm going to go to stat, test, and this one is the 2 mean t interval. So I've got 2 samples, I'm trying to estimate a mean, and it's the mean difference, and so I'm going to use t, and then I'm trying to construct an interval. That is stat test 0. It says 2 sample t interval on your calculator. So the first thing it's asking you for is, do you have data or do you have stats? So this chart right here gives us the stats that we need, so we're going to go to stats. Now it's asking for x bar 1. X bar 1 would be the mean for the sweetened. So x bar 1 is going to be your 6.41. Standard deviation for 1 is going to be 5. Sample size is 10. Next thing it's asking you for is x bar 2. So x bar 2 is going to be the mean for the unsweetened, so that's 5.2. The standard deviation for the unsweetened is 15. The sample size is also 15. It's going to ask you for your C level. So the confidence level that it told us here was 95. So we're going to put in 0.95. And then for pooled, again, we're always going to say no to pooled. Then you're going to hit calculate, and your calculator is going to take a second, and it's going to find the confidence interval for you, and you're going to see that the answer is B. All right, so that one's just a plugging it in the calculator and getting the answer. All right, let's look at number 4. Number 4 says, based on that confidence interval, so again, let's remind ourselves we had this confidence interval right here. Based on that confidence interval found above, which of the following conclusions would we make for the corresponding hypothesis test performed on the mean difference? All right, so remember for the hypothesis test, basically what that would be is we would have a null hypothesis that the mean for sweetened equals the mean for unsweetened against an alternative that the mean for sweetened does not equal or is different than the mean for unsweetened. So that means that we are looking at mean of sweet minus mean of unsweet equals 0 compared to mean of sweet minus mean of unsweet does not equal 0. So in this particular situation, since I'm looking at a difference, I'm looking to see whether or not 0 is in this interval. And so when I look at this interval, I can see that 0 is in the interval. Therefore, what we would do is we would not want to reject 0. So we would want to fail to reject the null hypothesis. And the reason that we're doing that is because that's our hypothesis of no difference. That's our hypothesis stating that at some point the sweetened and the unsweetened can equal each other. Therefore, we wouldn't want to reject that null hypothesis. So we're going to fail to reject the null hypothesis, and the reason is because 0 is in fact in that interval. So the answer would be A. So 0 being in the interval means that there's a possibility of no difference between the sweetened and the unsweetened. 0 not being in the interval would be that there's a possibility of a difference. All right. Cool. All right, number 5. This past fall, temperatures in a particular city seemed to fluctuate tremendously. The days often felt like summer and the nights often felt like winter. A weather analyst selected a random sample of 9 days from this past fall and recorded the high and low temperatures in this city for each of the days. So we have our chart here. Which of the following satisfy the normal condition so that the T procedures can be used for these paired data? This tells me that we're looking at paired data, which means that we are only going to look at the differences. None of the other data even matters at this point. So as long as I'm looking at the differences, the paired data, then I don't have to worry about whether the high and low temperature is normal, whether the sample size for high and low is a certain number. All I care about is the differences when I'm looking at paired data. So I'm just going to look at this difference column, and this is this difference row, and this is the only row that matters. So the distribution of high temperatures has to be normal. I don't care about the high temperatures because of the paired data. The distribution of low temperatures has to be normal. I don't care because it's paired. The distribution of differences must be approximately normal. That is true. The distribution of both high and low, nope, don't care. All 3 have to be approximate. Nope, they do not. I don't care about the high or the low. I only care about the differences. So the answer would be C. What would be the hypothesis for this paired t-test? Now, I'm going to have you guys assume something that is extremely unrealistic, but we're going to assume it anyway. We're going to assume the high and low are not different. Okay, so we're going to assume that we're looking at no difference. Very unrealistic, but that's what we're going to go with. Our null hypothesis would be the mean difference is equal to 0, meaning that the high and low temperature could equal 0, could equal a difference of 0. Again, very unrealistic, I know. The alternative hypothesis is that the mean difference does not equal 0. Most of the time when we're doing paired data, that's what we're looking for. We're looking for a mean difference equaling 0 versus a mean difference not equaling 0. And then again, I would define my mean difference. This would be the true mean difference in high and low temps. Again, I know it's unrealistic and I apologize about that, but we are looking at the mean difference being 0 versus the mean difference not being 0. All right, and then it tells us to actually conduct this test and to get this test statistic. So number 7 says, assume that the conditions are met. So we don't have to make a box plot. Yay! Assume the conditions are met, and we're going to calculate the t-test statistic and the p-value. So again, what would we do? We would take these differences and we would plug them into L1. So we're going to put the data into the calculator. And then we would go to stat, test, and this is going to be under number 2 for just the t-test. This is like a one mean t-test, but for the differences. So we're doing a one mean t-test, but just on the differences. So again, data needs to go into L1. Then you'll go, after you put the data into L1, you'll go to stat test 2. All right, and it's going to ask you, do you have data or do you have stats? You have data. It's going to ask you, what is your mean that is claimed? And you're going to put in a 0. Your mean that is claimed is 0. The list is L1. The frequency is 1. So you have your list is L1, your frequency is 1. And you'll have your calculate. Oh, and then it's going to ask you what is the direction of the hypothesis. So that would be mu does not equal mu not. and then you'll calculate. Okay? All right, I'm going to scroll up here so I can write down the answer. All right, so again, you did stat test 2, and you did calculate, and here's what you should have gotten. Your t-test statistic is very large. Your p-value, 6.15 times 10 to the negative 10th. That is a super, super small p-value. Your degrees of freedom, remember that's n minus 1, so that would be 8 because there's 9 data values. And so now it says that we should conclude. We should make the appropriate conclusion. So the p-value equals a super small number, and that is less than the alpha of 0.05. That's our significance level that it gives us. And so because the p-value is so low, we're going to reject that null hypothesis. And the reason that we can reject the null hypothesis is because there is convincing evidence that the true mean difference is different than 0, which we should not be surprised. We should not be surprised that we have such a big t-test statistic and such a teeny tiny p-value, and that is because of the fact that we have a big difference between the high and low temperatures. It's way different than 0. Most of those differences were in the 30s, and so we have a very large p-value, very large t-test statistic, a big difference, and then we have a pretty small p-value. All right. Cool. Let's keep going. Number 8. Find the t-star critical value using the information that is given here. All right, so we're going to find some t-star critical values. So t-star critical value for 95%. So that means I've got 95% here in the middle. That means I've got 2.5% on each side. Therefore, my area of this left side area is 0.025. To find a t-star critical value, I'm going to use inverse t. That is under second vars. It's underneath inverse norm. This is your inverse t. The area is 0.025. Your degrees of freedom, df, is n minus 1. Since n is 19, that means our degrees of freedom is 18. You'll plug that in. When we are getting t-star critical values, just like we did with z-star critical values, we don't need the negative. So we are going to drop the negative when you get your answer. And when you plug that in and you hit enter, you get 2.1. That would be our t-star critical value for 95% with 18 degrees of freedom. All right, next one. Our 90% confidence with a sample size of 27. So I've got 90% in the middle. That means I have 5% on either side. That means I have an area of 0.05. My area here is 0.05. I'm going to use inverse t. Area is 0.05. Degrees of freedom would be 26. There's 27 in the sample, so I would have a 26 degrees of freedom. Okay. Plug that in. Again, when you get your answer, you're going to drop your negative, and you get 1.7. 98% confidence. I've got 98% in the middle. That means I have 1% on either side. I have an area of 0.01. N is 50. Inverse t. Area is 0.01. Degrees of freedom would be 49. Plug that in, and you'll get your answer. You're going to drop the negative, and you should have gotten 2.4. Make sure you can do inverse T, second vars, inverse T. You're going to definitely need that on your test. Let's look at number 9. Number 9 says, a researcher wishes to compare the average amount of time spent in extracurricular activities by high school students in a suburban school district with that of a school district in a large city. The researcher obtained an SRS of 60 high school students in a large suburban school district and found the mean time spent in extracurricular activities per week was to be 6 hours with a standard deviation of 3 hours. The researcher also obtained an independent SRS of 40 high school students in a large city school district and found the mean time spent in extracurricular activities per week to be 5 hours with a standard deviation of 2 hours. Suppose that the researcher decides to carry out a significance test to see if there is a difference between the suburban and city districts. What hypothesis would you use to carry out the significance test? Be sure to define any parameter of interest. In this problem, we have two very different groups. We have the suburban versus the city. So we have two groups, and we are looking to see if each group is different as a whole. So I'm not pairing anything up. So this would be a 2 mean t-test. My null hypothesis here would be that the mean of one is equal to the mean of the other. The alternative is that the mean of one does not equal the mean of the other. Now, I can use, if you guys want, you can use subscripts that basically define the words. So if you wanted to use mu sub s and mu sub c for city, that would be fine. Either way, it doesn't really matter. All right, so mu1 is the true mean time in extracurriculars at suburban school, and mu2 is the true mean time in extracurriculars at city school. All right, and those are our hypotheses. Okay. All right, number 10. The weights in pounds of adult women are approximately normally distributed. A random sample of 18 women is taken and the following statistics are found. X bar is 127, standard deviation is 15. Calculate the standard error of X bar. The standard error of X bar is equal to the standard deviation of the sample divided by the square root of the sample size. So I just need to plug in the standard deviation of the sample divided by the square root of 18, and that will get me my answer. This is just a formula, and you got to plug it in and go. Standard error is the standard deviation of the sample divided by the square root of the sample size. 3.54 is your answer. All right, our final section here, we are going to find what procedure would we use for each of these, okay? So which procedure would we use for each of these? We're going to be specific. We don't have to carry out the test. We're just going to find what procedure. All right, so first one. Do people smoke less when cigarettes cost more? A random sample of 500 smokers was selected. The number of cigarettes each person smoked per day was recorded over a 1-month period before a 30% cigarette tax was imposed, and again for 1 month after the tax was imposed. So what's happening here, you guys, is that I have a single random sample. So I have one sample of 500 people. And what we're going to do is we're going to look at some data. It's the number of cigarettes that they smoked before, and then we're going to compare it after. So each person is going to have two data values, a before and an after. So there's going to be two data values for each person. That sounds like we have a matched pair design. So this is a matched pair design. That means we would use a paired t-test. I'm going to test to see if there's a difference between their before and after smoking habits. B says, how much greater is the number of pencils that seniors carry in their backpack compared to the number of pencils that freshmen carry in their backpack? Random samples of 100 seniors and 100 freshmen were selected, and the number of pencils in their backpack was noted. I have two very clear samples. I have two groups here. All right, so I have seniors versus freshmen. And I'm only collecting one value per person. I'm just finding out how many pencils each person has. That's only one value per person. And the big note here is I am estimating how much greater the number is. So I'm estimating a value. That tells me right there that I'm going to use an interval. Since I have two samples, this is going to be a 2 mean t, and then we are making an interval. This would be a 2 mean t interval. All right, let's look at C and D. C, you have data on rainwater collected at 16 locations in the Adirondack Mountains of New York State. One measurement is the acidity of the water, measured by pH on a scale of 0 to 14. The pH of distilled water is 7. Estimate the average acidity of rainwater in the Adirondacks. All right, so we took a single sample of 16. So we have one sample of 16 locations. We are collecting the acidity at each location. So that is one data value per location. And it says that we're estimating. All right, so we are estimating. Again, that's going to tell us we're doing an interval. This time, however, we just have one sample. So this would be a 1 mean t interval. This would be a 1 mean t interval. Number D. Yep. Consumers Union wants to estimate the mean difference in the number of hours that teenagers are on their phone during the school year versus the summer. So we're doing school year versus summer. They take an SRS of 50 teens and notate their average screen time during the first week of school. Then they take a separate SRS, that should say S, of 50 teens during the month of July and notate their average screen time. So it looks like we have two separate samples. We've got a sample of 50 teens during the first week of school, and it says they're taking a separate one. So we're not matching up these kids. We're not looking at the kids versus each other. We're looking at 52 different groups of 50. So this is two groups. And we are only collecting the number of hours that they're on their phone. So we're just getting one data value per student. And it says we're estimating a difference. We're going to estimating a difference. So if I'm estimating, that means I'm doing an interval. I've got two groups, so this would be a 2 mean t interval. This is a 2 mean t interval. And finally, do roller coasters really go 60 miles per hour? You test the speed of a random sample of roller coasters across the country and to find out if you have convincing evidence to show that the average speed is actually higher than 60 miles per hour. So we're just taking one sample, all right? We're going to take a random sample of some number of coasters, and we're going to just collect the speed. So we're just getting one data value per coaster. And we are testing a specific value. We're testing to see if it's 60 or if it's higher than 60. So we are testing a value. This would be a 1 mean t test. That would be a 1 mean t test. All right, you guys, make sure you guys are prepared and good luck.